Oh, thanks. Thanks, Artem. I was thinking of you. I'm pretty sure I started, but let me double check. Okay, so it says pause. That means I am recording. Alrighty. Now, we've done these kinds of filters, right? And maybe there's some gain, right? We've exchanged this for that. This was the high pass, right? I'm just saying there's an op amp here, right? I'm not going to draw the whole thing. And this was low pass. And when we first did that on midterm 1, the op amp was modeled like this, right? Right, that was the op amp model. Now, in general, on any interview, that's kind of the first, you're going to do that, right? This is ideal. It's non-inverting. That's a non-inverting op amp with a gain of 1 plus R2 over R1, right? That thing, first thing you learned in EE98 or your original circuits class, yeah, that will be your first thing. So some of the questions I'm going to go over today, yeah, this is the assumption, right? That I'm going to design a circuit, I'm going to design a low pass filter with a certain gain. I'm going to design a high pass filter with a certain gain, right? And it's all predicated on the fact that, right, that let's take the simplest high frequency model of an op amp, 2 pi gain bandwidth divided by S. All right. Because really, you just have to kind of stay here. Now, if I'm testing this with if I'm testing with a step function, well, the Laplace transform of that is 1 over S, so there's infinite frequency. So when I test this circuit with a step function, yeah, there will be a response outside of this, right? It'll happen. But if I normally am going to keep my signals in that range, yeah, I can get away with these simple models, right? You always start simple, then go more complicated, right? And that's the gain bandwidth, and that would be 0 dB. Now, if you've designed a filter, you do a step function, and then something isn't working, like ringing, Oh, then you start using these more complicated models to get to the bottom of it. All right. So so this is what we want to find out. All right. Well, in order to get there, we actually want to stay or start, if you will, in the Laplace domain, right? And so, yeah, I can label some voltages x1. I'll call that x3, x4, and that's out. But you can see these are buffers, right? And so x4 equals x1. That's a buffer too. V out equals V at x3. All right. So you don't have to re-derive the buffer, right? And yeah, the buffer, non-inverting and inverting gain stages, those will have to be memorized, right, for job interviews and really life as an electrical engineer in the field. All right, so what's Vx1 is just the voltage division of all right. So then we put in 1 over SC, right? ZR is R, 1 over SC. Pull out the RC, multiply through the S. All right, 100K times 10U should give me 1. So 1 over 1 or 1, it's the same. So that's omega naught is just 1 radian per second. All right. Well, we can see that Vx3 in this case equals the same thing because look, 100K, 100K, 10 microfarad, 10 microfarad. All righty. Well, So the beauty of op-amps in the Laplace domain is I find this transfer function, I find this one, and multiply them together, right? That's how I get to here, right? That you should be pretty familiar with that. So the transfer function would be omega naught squared s plus omega naught squared. So just looking at that, it's a filter. What kind of filter? Low, high, medium, low pass? Okay. Because if I set s equal to 0, omega squared divided omega squared is 1, right? If I let this go to infinity, right, this will all go to, the magnitude will go to 0, right? So it's low pass, yep. What order system is it? Second. So second order systems can be in control. Well, actually, any system, right? Even an integrator is unstable. So is it stable or unstable? Okay, well, let's just look at it. There's two roots here, right, at omega naught, right? And they're both real. I know I have trouble showing two roots at the same spot, but hey, that's less. The real part is negative, right? So it's stable. If I multiply this out, I get s squared plus 2 omega naught plus omega naught squared, right? And, oop, I missed the s. All right, the s squared is there, the s is there, and the constant term is there. That should be stable. I put in 1 squared, 2 omega naught times 1 plus some constant. The sign doesn't change. It's stable. I mean, that's like the easy way to check. The y is that e to the minus omega naught t, exponential decay. Over here, you would have e to the omega naught t, right? Now, of course, there's two roots here, right? So there should be two exponential decays, but in fact, they're at the same spot. So there's going to be a t there, right? Now, is it critical over or under? Critical. Now you might ask, hey, what happened to the damping coefficient? Well, in this case, zeta equals 1. So it's in there. All right. Now, yeah, in this example, omega naught is in fact where the root is. When you have two distinct roots, omega naught is where you're at minus 90 degrees phase. Same here, but well, I'll just show you later. Okay. So the magnitude, it's going to be 0 dB, right? Because at DC, this over that is 1, 20 log of 1 is 0 dB, right? It comes out to omega naught, and then notice, hey, it's second order right at that spot. Instead of minus 20 dB, it's going to be minus 40 dB per decade, all right? So I'm just going to do this and call that minus 40 dB. Now, we can't use this to do our system extraction, right? This is the asymptotic Bode plot. Because in reality, what will it really do? It'll do this, and it'll be minus 6 dB down. So, hey, I mean, how do you find the damping coefficient? Well, you find omega naught, which is what? Where the phase is 90, okay? Then you read off the gain there and use the gain at DC and then come up with it. But here, in this case, the gain at DC, the gain at omega naught would be 0 dB, same as here, and you'll get a nonsense answer. So you really have to use you can't use these asymptotic plots to do the system identification. All right. Now, just to kind of reiterate what I said is, hey, omega naught, that's where we're at minus 90 degrees. So at omega naught divided by 10, that's where it starts to kind of go down. At omega naught, it's minus 90. 10 omega naught, we're at our full minus 180, right? Each order causes 90 of phase. And a high pass, it causes like a plus 90 of phase, and a low pass, it causes a minus 90 degrees of phase. All right. So as rough as this is, you know, that's a pretty, it shows me everything I need to know. Omega naught, right? The only thing I need to, I can tell that's a decade, right? And then it went down 40 dB, or I can just make it easy on myself and just say minus 40 dB per decade. All right. Now that pretty much tells me everything I need to know about that Bode plot, right? It's a low pass filter. Remember, we wanted the transient response to a step, okay? So V out should equal 1 over S times H of S, which is 1 over S times omega naught S. Now, it is possible to use partial fraction expansion and then use a simple Laplace transform table. I tend not to do that because it's right there, right? Here's S times a single pole. here's just an exponential, 2 exponential decays. Here's s times 2 exponential decays. And here we go. It's right there. Except, yeah, it's one. We don't have an a squared term over here. All right, which we're just going to get these two things. Okay. So everything is exponential decay. So everything goes to 0. This is a low pass filter. So if I put in 1, right, eventually I should get 1. Well, there's my 1, right? Then I'll have 1 exponential decay here. Oops, exponential decay. But then I also have, it's second order, so there's got to be 2 exponential decays, right? But rather than 2 separate, like an omega 1 and an omega 2 or an A and a B, well, it's the same root, just repeated. So that's where this stuff creeps in. And I'm just, yeah. Yeah. So in this case, all right, V out of t equals 1 e to the minus t. Omega naught was 1. So we get t e to the minus t. Now, I think these kinds of things are hard to plot, right? But you know it's going to be, you know it's going to start at 0, right? Because 1, t at minus 0, e to the 0 is 1, 1 minus 1 is 0, but this is 0 times 1, right? And then we know for long periods of time, this is going to decay, right? And then this will decay, right? Now, the thing is this will kind of decay more slowly because the time is as time goes up, this is going up linearly, but this is going down exponentially, right? So this will probably be the dominant term. Well, this just decays, all right? But we know that at some point in time, it's going to be constant. Well, how are we going to get there? Well, really, I'm over exaggerating, right? Like it could, right? You have this kind of little S part, right? And what I've found is, you know, it all depends where you take it. But in about 6 to 10 seconds, it'll be here. It's not like there's this universally adopted standard of 5 tau, right? But I would accept, I would accept this as an answer because to really plot it, you kind of need a graphing calculator or something. But the fact that, yeah, omega was 1 radian per second, it's going to take about 6 to 10 to get here. And I mean, even though I'm a little sloppy, you can tell that if I mean to show that there's ringing or oscillations, you can definitely see that, right? Now, and yeah, there's the peaks decay. These peaks are decaying exponentially. All right. So let's see. All right, phase goes from 0 to minus 180. Oh, that's good to know. Where's omega naught? Minus. Okay. So it might be hard to see, but I'm at about minus 6 dB and about minus 90, which is indicative that it's a critically damped second order critically damped system. And the frequency is 161 millihertz, which it's really, I gave omega naught is 1. So the frequency is 1 divided by 2 pi. All right, so now you might see in a lot of my examples, I work it out so that it's a nice even number to read off of the chart. All right. Okay, that seems to verify that what I was doing was correct. Let's do a pulse, step response. We'll start it at 0. Since it's a buffer, it's not going to go above the power supply. I tend just to put in small numbers from here and then leave a large number there. All right. Now, simulate. Transient. How long should I simulate for? Well, if a first order system had an omega naught of 1, right, that means tau is 1, I would simulate for 5, right? This isn't quite, it's not the same, right? So I couldn't just put 5, but I'm going to put like 10 times tau, even though it doesn't, like tau doesn't really, there's 2 taus, right? One scaled by t and the other one not scaled by t because there's 2 exponential decays. Oh, my bad. So therefore I should have left the voltage supply on, right, for 10 seconds. Oh, all right. So you see that kind of shape, right? A first order system would just have a straight line. At 5 tau, you know, I'm 0.95 volts. Right? Well, so 5 tau in a first order system, you should be at 0.99, right? So what would the equivalent tau be? Six seconds. So does that mean every critically damped thing, instead of 5 tau, it'll be 6 tau? It seems like it, but I think on job interviews, people, you would lose them. And they say, no, tau is first order system, right? and that's kind of with the understanding that 5 tau is somewhat of an arbitrary standard, right? E to the minus 5. It could have been e to the minus 6, right? Because even e to the minus 5, it's not really settled to where it's going, all right? But it's not 100 seconds or like milliseconds, so that it was a good estimate of how long to set the square wave for. And you saw me mess it up. I put in 1, right, and it looked it looked like a bandpass transient response. All right. So come on. Now I have a high and I have a low. I probably should get some kind of bandpass response. And I do. Because a bandpass, right, it's blocking frequencies in the middle, right? So that means it's trying to block DC, and you can see that over here, right? Because it's going back to 0, right? It blocks high frequencies because notice it doesn't instantaneously change up and then you have an exponential decay, right? But notice that omega naught, right, which caused our tau, I didn't change the simulation time, but yet I'm capturing the whole thing, okay? Now, yeah, simulate, go back to our here. All right, there's a bandpass looking shape. All right, omega naught will still be in the same spot, even though, except it'll be 0 degrees phase rather than minus 90. All right. Now I should have high pass. Omega naught, it's at plus 90 this time. And then when we do our transient, right? There is our almost instantaneous change, exponential decay. It does shoot below zero once and then settles. So that is definitely indication of a high pass second order, critically damped, near critically damped. Could be a little under damped, could be a little over damped. 0.1, a damping coefficient of 1, 0.9, 0.8, or 1.2 can be very hard to tell by eye. All right. Now the Bodhi pot, you can't really hide, right? If you calculate that damping coefficient, it tells you what it is. And I guess that's the really good thing about the Bodhi plot, is once you have that data, you can't really hide. Now, oh, stupid thing. I was trying to make a quick notch filter. So it passes high frequencies because it changes almost instantaneously, but then it kind of goes down to zero, so maybe not. No. Okay. That's okay. So some things that I want to point out is that I showed you a high pass, showed you a low pass, and a band, right? Second order, critically damped, right? But here's the thing. They all had the same denominator. Depending on how we arrange the resistors, the high pass was S squared. This should be omega naught S, right? Now, yeah, there'll be the damping factor in there as well, but this time it's just 1. And then we have omega naught squared. So the phases, that one repeated pole meant that at omega naught, which you can read straight from here, right, was where you were going to have that 90-degree phase. Now, yeah, here it was going to be at the plus 90. Here it was going to be at the 0. And here it was going to be at the minus 90. Yeah. Oh, did I? Yep. Thanks. All right, that's where you extract it. Now, that's getting a little ugly here. Now, so if I were to draw the same circuit, yeah, I would get right, and you can see the two distinct real poles right there. But what happened to omega naught, right? Well, omega 1 times omega 2, that equals omega naught squared, right? So I can just put omega naught squared there. Then, right, I have s squared plus omega 1, omega 2, right? Then 2 omega 1. No, sorry. Omega 1 plus omega 2 times s plus omega 1, omega 2, s squared plus. Okay. Right. Now this 2 zeta omega naught equals omega 1 plus omega 2, omega naught squared equals omega 1, omega 2. And then you can back calculate it. And you're going to find that this will be greater than 1. All right. So we'll have two distinct real poles, right? One here and one there, right? It'll be minus, those will be minus roots, so it will be stable. So it's, all right. Now the thing is even though there's two distinct roots, I can still get, let's go back, right? This is low pass, the one I drew. Right? But if I replace this with s squared, it's going to be high pass. If I replace this with, some number times s, that'll be band, high, and already it's low pass. All right. It just would look, it would look different. So let me change this quite a bit. All right, so yeah. There we go. Although that is, Oh, that's right. So there's our low pass. Still not seeing. Okay, there would be our low pass. Yeah, low pass. But see, it goes in this particular example. I can see 1, 2, like 3 definite humps, but the phase goes down to minus 360. Okay, so you just say 360 divided by 94. It's a fourth order circuit. 1 RC, 2 RC. Should be second order, right? What about the op amps? Right. They have capacitor. So the reason this is going on is those op amps have capacitors that have feedback on the inside to prevent things like ringing, and so they are adding that. Now the thing is that's like an op amp with a 1 capacitor model. Okay, then you start getting a more complex model, and then minus 550 gets kind of wild, right? I'm not trying to blow your mind right before an exam, but when you test this with a step function, yeah, some of these things you might see. So let's actually do that. Actually, omega, probably like more on. Okay, now look, looks very straight here, so you might be thinking first order, but if I zoom in, I should see that a little bit better. All right. On the other hand, we're talking about a fourth order filter. I'm not, but notice that it doesn't seem to be having an effect. And yeah, these op amps aren't really, they're not ringing, right? Because they're not really getting a step response. This is getting an exponential decay, and then it's getting, this one's getting an exponential. So this is filtering the step function. So is this. In fact, so is this. So before it gets here, it's filtered 3 times, and then it's filtering itself the 4th time. So what I'm trying to say is notice how much analysis we did with just assuming an ideal op amp and how pretty good it was. But yeah, I'm good at choosing values to make sure that we're not running into it. We're not running into preventing that. Now, when you're working in industry, well, you're going to be going, you're effectively, you're going to be really trying to go to the limit, if you will, right? And you might have, when you're debugging a problem, hey, this should be a second order filter and it's not working. Or, you know, my RC filter with op amp should give me minus 90 degrees of phase. So I should be able to add another minus 90, almost minus 90 in a feedback loop before it starts to oscillate on me. But then all of a sudden it isn't. No, it's oscillating right there. All right. And this is a little bit what I was trying to say last time, is that if I have a summer, right, and then I have a transfer function, and I'm going to call it omega naught s plus omega naught, right? That's my out. And then I have my GS, right? Well, no feedback, right? V out over V in equals omega naught S plus omega naught when the magnitude of S is much, much greater than omega naught minus 90 degrees of phase. So on the Bodhi plot, right, if that's omega naught and this is 100 omega naught, right, I should be getting minus 90 degrees of phase. Anything below that, right, so that means I should be able to have another minus 90 degrees of phase. So I could have another transfer function, omega 2 S plus omega 2, right? Well, there's another 90 degrees of phase, minus 90. So that if I were to connect this, I could get, if the frequency were right, I could get minus 90 and another minus 90, and now I'm actually getting positive feedback. Now, of course, that will only happen if the magnitudes are greater than 1. But that's the whole thing with phase margin. All right. It's not on our exam, but I think they'll talk about it in 132 and 124, and you can look it up, you know, like right before a job interview, because industry likes to talk in terms of phase margin. Any questions? Alrighty. All right, people have started to leave, so